Hello, I'm going to walk you through an epidemics model, how to set it up, analyze it and run it, doing a simulation of the model, all using the Patrinet formalism. So our model is here shown in the first slide. It's a model that has three types of interactions formulated in the yellow box in 3 lines. And below the box are stated the players or species in that model, and we have 4 types of species. So you could think of humans in the case of an epidemic. So we have susceptible identified by S, infected denoted I, the contact pair which is Si, and we have recovered people denoted by R. So what we are going to do is we're going to set up this model using the definition of its stoichiometry matrix, then look at the T and P invariants of the matrix, and finally do a simulation of the time course of each of the species involved. So let's go through the assumed actions or interactions line by line. So the first line tells us that in order to form a contact pair, what we need is a susceptible person and an infected person. So then we assume if they get in touch with each other, and in parentheses exchange a virus, then they form an Si pair. The second action is actually the dissolution of that pair. So Si goes to an infected, which was the old infected, plus a new infected, which is the former susceptible person. So Si goes to I plus I. And the third action is the recovery process. After a certain time, an infected person can be converted to an R, which is a recovered person, and so to speak, an immune person that can no longer be affected. So it's a very simple thing. There are lots of assumptions that we haven't put into a model, but it's sufficient to show how things work. So let's try and get this into code and analyze and simulate it there. So set up a new MATLAB window, save it as SIR model, for example, and having that model saved, I can now fill in a couple of things. So the first thing I want to do, I want to put into the code a reminder of what the actions and the species were. So I'll just copy that in here. So the actions are 3 actions that define our assumptions about what is happening, and the species are the 4 species that we assume to be interacting according to that model. So we skip over the generation of an input and an output vector and then the construction of an A matrix. We directly set up the stoichiometry matrix. So zeros, how do we set up a stoichiometry matrix? We need the rows. Number of rows is equal to the number of species. So we have 4. The number of columns is equal to the number of actions, which is 3. So our matrix will be a 4 by 3 matrix filled with zeros initially. And then we have to fill in the individual contributions. So stoichiometry matrix means to show what are the net changes in every reaction for every species. So let's fill in for the first reaction what happens to the first species in the first reaction. That's the element 1, 1. So first species is susceptible people, and we can see susceptible meet infected and form a pair. So the number of susceptible people will go down by 1. And the number of infected people in the first reaction will also go down by 1, because we need 1 of each. And what we'll get is a member of the third species, which is the contact pair, and according to that reaction number 1, it will increase by 1. So if I execute this code and show it here at the bottom, our stoichiometry matrix has now all the components implemented that have to do with the first action. Okay, so let's continue, do the rest. How about the second action? And that is the contact pair will dissolve. So the contact pair is species number 3. In the second action will dissolve means it will decrease by 1. And what happens? What do we produce? We produce 2 infected persons. So the species number 2 in that second reaction will increase by 2, right? We get 2 out of it. That's what it says here. From one contact pair by dissolution we get 2 infected. So that should be number 2 added. We can now see it implemented in the command window below, and in the meantime I'll start finishing all the entries. So eventually the infected people will turn into recovered. So in the third reaction infected people will again decrease by -1, and at the same time species number 4, which are the recovered, in the same reaction will increase by 1. And that gives us the final stoichiometry matrix with all entries according to that model. Assuming that is all done well, we can now go to analyze that stoichiometry matrix and look at its invariants. Can you remember how to get the invariants? For example, the T invariant is something that you get from the null space of the stoichiometry matrix. Now we can do the rational argument and have that code executed while we think about what does it mean. T invariance means how many elementary fluxes are there, or what combination of reactions leads to the number of persons being unchanged. Well, the answer is empty matrix. It means none. There isn't a combination of those actions that we have included that will not lead to a change in species numbers. So that's one thing. So let's then check the P invariant. How do we get the P invariant? Similarly, it's the null space. We need the A matrix, the reaction matrix. And if we set it up in a similar line, we actually get an error. Why do we get an error? Because we have never defined the reaction matrix. But that is simple to mend. There's no trouble here because we know the A matrix is nothing but the S matrix transposed. So if we put in S prime instead of A, that should give us the correct result, and we can see the correct result directly. We get a single P invariant. It's specified here as 1121. And you remember that's a way to calculate the number of that conserved moiety, so to speak. So these 4 species taken together will add up to a number that is unchanged. That strange number 2 here, you can actually get rid of it because you will see that if adding 2 times the number leaves the thing unchanged, and also adding 1 times the number will equally lead to an unchanged number of species. And the interpretation of this is that this reflects that according to this model, the total population, so the sum of susceptible, infected, contact pairs and recovered, remains unchanged. So there are no births, no deaths, nobody moves into the country, nobody leaves the country, and that's why we have one conserved moiety, which is the total population. And finally, we can try to do a simulation of that model, and I'll show you how it's done. I'm not going to do all that code. I have prepared some code, which I'm simply going to copy and paste here. But before we do a simulation, I'll go through it and explain what's happening here. So the code for doing a simulation first defines the number of steps, and that's time steps. So we want to look at a simulation of, in this case, 20,000 time steps. Units are now arbitrary. Think of it as, don't know, hours maybe. Results. In the next line, we'll set up the results vector or results matrix as zeros, and we specify our initial species vector. We say at time 0, you have a population that is defined by 20,000 susceptible people, 11, let's just change that to 1. Let's make 1 infected person in that population, no contact pair, and no recovered person initially. Let's just assume these are the numbers that we want to do our simulation with, and then we need to define the rate constant. So how quick are those processes? It's this line here, the u vector. So what I have done, I've arbitrarily set first and second rate to be happening at a constant, at a time constant, which is equal to 1. It's just arbitrary number here. But I have then assumed that the third, which is the formation of recovered species, is slow compared to the first two processes. So it will take a longer time to recover than to form a contact pair. And once we have set this up, we are ready to do our simulation. Simulation is done in a for loop, very similar to what you did with the Fibonacci number generation. And then we plot the results, and that's it. So let's try what happens. Let's just execute the code, and here we see the result. Quick walk through the result. The blue line starts at 20,000, goes down to 0, so that linear decrease shows the temporal evolution of the number of susceptible people in that simulation over 20,000 time steps. At the same time, if we look at the red curve, which is the infected people, that number goes from near 0, it's actually 1 initially, and then goes up to reach on the order of, I would say, 18,000 within those 20,000 steps. What is a nice feature of this model is that the number of contact pairs, due to the setup of the rate constants, at any time is very small, and in fact is close to 0. That's the yellow line. Finally, we have the magenta line. That's the number of recovered people, which is initially 0, then stays very low but keeps coming up, and it's just a slow process. After people get infected, the number of infected still increases, but then with a certain delay and with less slope, also the number of recovered people goes up. Well, that's about it. There's no more dynamics that you can get out of this model. Only the quantitative proportions of those lines can change. And of course, this is not yet done perfectly, because there's a lot of things that we have not considered. We've not considered people coming in, people going out. We've not considered recovered people might become susceptible again, and so on. A lot of things that you could add. But we have gone through the whole cycle of assuming, making assumptions about what happens in an epidemic, to actually predicting quantitatively the numbers over a certain range of time using a simulation of that stoichiometry matrix.